Alright, so far we have covered topic 1. We have reviewed most types of the functions, and from today on we're going to have a look at the second topic, limits and continuity. So in this topic we'll cover the following sections. First, let's have a look at why we need to learn limits and continuity. Well, suppose we have a function fx, okay? And let's suppose part of the graph of fx looks like this. And we have two adjacent points, P with coordinates x and fx, and Q. Coordinates are x plus h and fx plus h. Then we know the slope of the secant line between P and Q is given by delta y over delta x, right? And delta y is fx plus h minus fx, and delta x is x plus h minus x. So this can be simplified to fx plus h minus fx over h. Of course, because P and Q are different points, so h is not 0. Also note that when h approaches 0, delta y over delta x will approach the slope of the tangent line at point P, right? In that case, Q is as close as possible to the point P. So when h approaches 0, that means the distance between these 2 points is very small, but they are still different points. So this is called the instantaneous rate of change of fx at point P. Actually, it has a special name. It's also called the derivative of fx at point P, which is denoted as the limit of this expression when h approaches 0, or fx prime, or dy by dx. So the three notations here all mean the instantaneous rate of change of fx at point P, or the derivative of fx at point P. So as you can see here, in order to learn derivative, we need to learn limit, because derivatives are defined using limits, right? Also note that this concept is only applicable when such limit exists at point P, which is not always true. We'll discuss this more in the following sections. Okay, clear? Alright, so basically, in order to understand derivatives, we need to understand the limits first. So next, let's have a look at the limit of a function at a certain point. We'll start to learn this concept by looking at an example here. The value of function f approaches as its input x approaches some value is said to be the limit of f. So limits are essential to the study of calculus, and as well as we will see, are used in defining continuity, derivatives, and integrals. So suppose, let's consider this function fx equals x squared minus 1 over x minus 1. Notice that x equals 1 does not belong to the domain of fx, right? X cannot be 1, otherwise you will have a denominator 0. Regardless, we would like to know how fx behaves close to the point x equals 1. So we can start a table of values like this. It appears that for values of x close to 1, we have that fx is close to 2. In fact, we can make the values of fx as close as 2 as we like by taking x sufficiently close to 1. We express this by saying the limit of function fx as x approaches 1 is equal to 2, and use the notation below to illustrate this concept. So this means the limit of the function fx as x approaches 1 is 2. Alright, so next let's have a look at an intuitive definition of limit. This definition is useful but not very strict in the sense of mathematics, but to the current stage, as long as you can understand this, you should be fine. So in general, we write the limit of fx when x approaches a equals L. If we can make the values of fx arbitrarily close to L by taking x to be sufficiently close to a on either side of a, but not equal to a. Of course, in mathematics, we have a more rigorous way to define the limit, but we're not gonna talk about it here. If you're interested, we can discuss this later after this class, okay? But here, as long as you know the intuitive definition, that's fine. Okay, next let's have a look at one-sided limits at a certain point. We'll have a look at an example here. So consider the following piecewise defined function. fx equals x if x is less than or equal to 1. fx equals x plus 1 if x is larger than 1. So we can easily find the graph of such a function, right? Apparently this is a piecewise defined function. So observe from the graph that as x gets closer and closer to 1, but from the left side, which means from this side. This is from left side of 1. Then x approaches positive 1, which is this point here, right? Similarly, as x gets closer and closer to 1 from the right side, which means from this side, then we will have a different result. fx approaches positive 2, which is this point here, right? So we use the following notation to indicate this difference. First, the limit of fx as x approaches 1 from the negative side. So we write it like this. This means x approaches 1 from the left side. So apparently that equals 1, right? And on the other hand, when x approaches 1 from the positive side, the limit of fx equals 2, which is this point. You see that? So the first limit is called the left-hand limit, and the second limit is called the right-hand limit at x equals 1. You see the difference? So sometimes, even you looking at the same point 1, you might have different left-hand limit or right-hand limit. This is called one-sided limits at a certain point of a function. So let's have a look at the intuitive definition of one-sided limits here. Again, these are not very rigorous, but intuitive definition for one-sided limits. In general, we write the limit of fx equals L when x approaches a from the negative side or left side. If we can make the values of fx arbitrarily close to L by taking x to be sufficiently close to a and x less than a, this is called the left-hand limit of fx as x approaches a. And similarly, we write the limit of fx equals L when x approaches a from the positive side if we can make the values of fx arbitrarily close to L by taking x to be sufficiently close to a and x greater than a. This is called the right-hand limit of fx as x approaches a. Did you get it? Again, like I said, this is a precise definition of limits at a certain point, but you do not have to understand this at the current stage. As long as you know the intuitive definition of limits and one-sided limits like this, you should be fine in this course, okay? So next, let's use an example to check your understanding of limits or one-sided limits. So suppose we have a functions graph like this below. Can you evaluate the following four expressions? First, the limit of fx as x approaches 4 from the left side. What is this value here? And B, what is the limit of fx when x approaches 4 from the positive side? C, what is the limit of fx when x approaches 4? Then what is f4? Alright, let's have a look at solution together. First, the limit of fx when x approaches 4 from the negative side refers to the limit as x approaches 4 from the left side, right? So tracing along the graph from the left, we'll see that y value that is being approached at x equals 4 is negative 2. Therefore, the left side limit when x approaches 4 is negative 2, right? And similarly, the limit of fx when x approaches 4 from the positive side is also negative 2. Because both the left hand and right hand limits equals negative 2, we can also say the limit of fx when x approaches 4 is negative 2, right? And the last one is the image when x equals 4. Of course, when x equals 4, you can observe f4 equals negative 2, right? Okay, so next let's have a look at the connection or relation between limit and left hand, right hand limits. So there is a theorem states that the limit of fx equals L when x approaches a if and only if the left limit when x approaches a equals the right limit when x approaches a, and both of them equals L. And a consequence of this fact is that if the left side limit, if the one-sided limits are different, then the two-sided limit limit of fx as x approaches a does not exist, often denoted as DNE does not exist. Okay. Okay. Well, use the example to illustrate this concept here. So, suppose you are given a graph like this. This is a piecewise defined function, right? Can you determine each of the following for graph B? First of all, what is the limit of gx when x approaches 2 from the negative side? So when x approaches 2 from the negative side, this function will approach this point here, right? So that equals 3. What is the limit of gx as x approaches 2 from positive side? That means from this side, right? So the function will approach this point, which is 4. And of course, we can see the left limit does not equal the right limit, right? So the limit of gx when x approaches 2 does not exist, right? And last one, what is g2? g2 is the image of that function when x equals 2. So apparently that's this point here, right? And that equals 3. You see the difference? Also, we can have limits at infinity. So let's have a look at the definition, also the intuitive definition of limits at infinity. In general, we write the limit of fx when x approaches positive infinity equals L if fx can be made arbitrarily close to L by taking x large enough. If this limit exists, we say that the function f has the limit L as x increases without bound. For example, if we consider this function here, we can say the limit of the function 1 over x squared when x approaches positive infinity equals 0. You see that? Because when x approaches positive infinity, x squared will approach positive infinity, right? So 1 over x squared will approach 0. And similarly, we can write the limit of fx when x approaches negative infinity equals m. If fx can be made arbitrarily close to m by taking x to be negative and sufficiently large in absolute value. If this limit exists, we say that the function f has the limit m as x decreases without bound. For example, if we consider the same function 1 over x squared, when x approaches negative infinity, we know x squared will approach positive infinity, and therefore its reciprocal will approach 0, right? You see that? And we can also define infinite limits like this. In general, we can write the limit of fx when x approaches a equals positive infinity if we can make the value of fx arbitrarily large by taking x to be sufficiently close to a on either side of a, but not equal to a. Similarly, we write the limit of fx when x approaches a equals negative infinity if we can make the value of fx arbitrarily negatively large by taking x to be sufficiently close to a on either side of a but not equal to a. So for the first definition, we can consider this example, the limit of 1 over x squared when x approaches 0. Apparently the denominator will approach 0 from the positive side, right? Therefore its reciprocal will approach positive infinity. Can you see that? And the other function we can consider for the second definition is the limit of negative 1 over x squared. When x approaches 0, we know x squared will approach 0 from the positive side. And therefore, if you multiply that number with a negative 1, that will approach negative infinity, right? Therefore, we say the limit of this function equals negative infinity when x approaches 0. Did you get it? Okay, if you don't have any question, next let's have a look at the concept of asymptotes. Okay, actually we can use the concept of limits to define asymptotes. The line y equals b is a horizontal asymptote of the graph y equals fx if we have either limit of fx equals b when x approaches positive infinity, or the limit of fx equals b when x approaches negative infinity, right? And similarly, the line x equals a is a vertical asymptote of the graph of y equals fx if one or more of the following holds true. Any questions? Okay, note that unlike vertical asymptotes, horizontal asymptotes can be crossed. The graph, for example, px equals 3x squared minus 8x plus 7 over x squared minus 4x plus 5 has a horizontal asymptote at y equals 3 as shown to the right.